we're going to have 3/8. 4 plus 4, I'll put it in as 2 squared so we can see where we get the 4. 2 squared to the 4/3 power minus, I'm going to go through the same thing, but now replace the input with 0, minus 3/8 times the quantity, 4 plus 0 squared to the 4/3 power. We want to simplify our arithmetic, and so we would have 3/8. 4 plus 4 is 8. We're going to take the cube root of 8, which happens to be 2, so 2 to the 4th power. Again, 4 plus 4 is 8. Cube root of 8 is 2 to the 4th, minus 3/8, and we're going to have 4 to the 4/3 power. Now, we can continue with this. 2 to the 4th is 16. 3/8 of 16, 8 divides into 16 twice, so that's going to be 6. Minus, and there's not a real easy way to look at this. One way we could do is to, if we have 4 to the 4th power, it would be a 4 times 4 to the 1/3 power. This would be 3/8. There we go. Times 4, and then this would be the 4 to the 1/3, or the cube root of 4. If you take the approximated value of that, it would come out to be 3.619. Now again, don't lose track of what we can do with this. What we're looking at, it doesn't tell us to look at the area under the curve, but in fact, if we were to use the area under the curve, we would type in x times the cube root of 4 plus x squared, and we would look for area under the curve. We're only looking from 0 to 2, so let's look at a window that will go from, well, let's say negative 0.5 to 3, and we'll scale by 1. From well, let's say negative 1 to 5, scale 1. And if we look at that, our area, we're going to want to integrate find the integral from approximately 0 over to 2. And in fact, that area is close to 3.62. Okay, so let's go to our next problem. Okay, our next problem is finding the area of the region bound by the function e to the negative x, the function y equals 0, and then our two vertical lines x equals a and x equals b. So this is in the same thing as asking for the definite integral from a to b of e to the negative x dx. Now looking for a composite function, we know that the derivative of e to the x is e to the x, but this is not simply e to the x, it's e to the opposite of x. So the inside function on here would be the opposite of x. If we take the derivative with respect to x, we would have negative 1, multiply both sides by the differential dx, and again, all we need is dx, not the opposite of dx, so we'll multiply both sides by a negative, and we're ready for our first substitution. So substitution number 1. Because I'm going to do a substitution, I'm going to opt to just not put any values there, and instead I'm going to write this as e to the u times negative du. That would be the same thing as negative the integration of e to the u du. We know that if we are looking for the function that's equivalent to e to the u, it would simply be e to the u. And we would now need to integrate from quantities here, but we're going to just make our second substitution. So we'll do our second substitution, and we end up then with negative e to the negative x power, and now we're going to integrate from a to b. So we need to look at f of b minus f of a. That would be negative e to the negative b minus, I'll put this in parentheses because I need another negative here, negative e to the opposite of a. That would be the same as negative 1 divided by e to the b. We have two negatives, so plus 1 divided by e to the a. And we really can't look at finding a graph for this because we don't know what a and b are. But if we take the derivative of this quantity, we should get back to e to the opposite of x there. Keep in mind, though, that this is a single value, which is the area of the curve. So we really have to go back up here to find the derivative, and that derivative then would be the same thing as e to the negative x. Okay, let's move on to our last problem here. This is an application problem, and again, what we're doing with integration is, as an area under the curve, it's the limit of the sum of infinitely many rectangles. That idea of a summation over multiple intervals, or over an interval with multiple inputs, is what we're actually able to do with an application problem. So let's take a look at this, and we'll just take it bit by bit. We're told that the normal monthly rainfall can be approximated by this equation, this function. Now, the normal monthly rainfall. So we're looking at a variable of t. Well, what does the t represent? Well, first of all, r is measured in inches. T is the time in month when t equals 1 corresponds to January. So if you want to know how much rainfall the monthly, the normal monthly rainfall in January, you put a 1 in here, and we'd have, now it's a sine curve. And you know that on a sine curve it is cyclic, so we're looking at the basic sine curve to look something like this, where it goes from 0 to 2 pi. We are, of course, looking, and 2 pi is 6.28, but we're looking at a sine curve, and then we have some transformations that are going on. But 1 would correspond to January. Okay. So the first task is to determine the extrema of the function over a 1-year period. We're going to take these one at a time, and I'm going to move the others to another page. Okay, so we're going to first determine the extrema of this function over a 1-year period. Now, this is going to mean then that we want to take the derivative of this function. And again, you remember how we find extrema. We're going to take the first derivative, we're going to set it equal to 0, and find zeros of that. And then we're going to determine if they're maximums or minimums by taking the second derivative, placing the zeros of the first derivative into the second function, into the second derivative. If it makes the second derivative positive, it's concave up, hence a minimum. If the second derivative is negative, it's concave down, and hence we would have a maximum. So let's go through and take this derivative. We would end up with 0 for the first term, so we'll just put a 0 there. The second one, you've got the coefficient of 2.399, and we have the sine of this quantity. So the derivative of sine is cosine of that quantity times the derivative with respect to the input variable of that inside function. So our derivative would be 2.399 cosine times the cosine of 0.524t plus 1.3t, or 77. So we have that, times the derivative of this inside function be 0.524. Now, if we are looking at finding extrema, we would want to set this equal to 0. So to find, and we have to say possible extrema, we're going to set the first derivative equal to 0. So we have 0 equals, and I'm going to multiply these together and see what we've got here. And I'm coming up with, and you can verify this, 1.25708, the cosine of 0.524t plus 1.377. Now, if we're going to set that equal to 0, it really doesn't matter. I could have this information, this factor wrong, and still come up with the same value, that if this product, and we'll put this in brackets here so we can really see it, if this product is 0, then the only one that could possibly help me out is the cosine part of it. So 0 equals cosine 0.524t plus 1.377. Now, thinking about this, if we have that the cosine of an angle is 0, what kind of an angle, where on the unit circle do we have cosine to be 0? Well, cosine is 0 up here at an angle of pi divided by 2, or down here at an angle of 3 pi divided by 2. So we are wanting then to, let's say, set 0.524t plus 1.377 equal to pi divided by 2. So if we use the pi divided by 2, we solve this, and we can come up with that t is approximately 0.3698, or we could round that off to be approximately 0.4. If we use that 0.524t plus 1.377 actually is occurring down here at 3 pi divided by 2, then we would have that t is approximately 6.365, or rounding it to approximately 6.4. Now, the problem was to determine the extrema, and we have that these are possible extrema, and so in order to determine if they in fact truly are extrema, we're going to find the second derivative of our function. So we go back up here to the first derivative, and if we multiply those together, we have 1.25708. And then we need the derivative of cosine. Well, we know the derivative of cosine is negative sine, and we're going to have it of 0.524t plus 1.377. And then we need the derivative with respect to t of this inside function, and we'll do that right now. And we end up with a second derivative of 1